turn it over to Marco.
Well, thank you so much for the kind introduction and the opportunity to talk to you all. I hope the sharing works. Everybody can see my slide. I need to confess first that I'm out of practice having a live audience. I've been teaching asynchronous the last 2 months, and it's a monologue, and the only feedback I get is my echo, basically. But if you do have questions or comments or so, do interject that at any given time. I'm not offended. I actually, at this point, I really love feedback to hear that at once. So my title here is Project-Based Learning in Engineering. I thought before I start giving some of those ideas that I try to follow, I want to talk a little bit about the problems that we try to solve in our field in engineering, and particularly in mechanical engineering. So I created this slide here, and it violates my standards for slides. It's supposed to have more figures and pictures than text, but I consider the small font text as a picture. It is taken out of the engineering and training manual that our students receive, our senior students receive, as a guide of what are the topics that they have to study and be able to master when they take the engineering and training exam. This is an exam at the end of their study, the undergraduate study. It is a requirement for them to ultimately become a licensed engineer. And the licensing that happens 4 years down the road, if they have 4 years of industrial experience, then they can take that exam. So this small font is my figure. It gives you topics that are part of that exam, and it's not a complete picture, but I want to point out some of these topics. There may be a chapter in the book, or there may be a part of a chapter of a book, but some of these items are an entire class. And so we have to accommodate all of these topics in order to prepare them to get licensures ultimately. And so we're facing a problem here. One is that the state of Idaho is pushing a 120 credit hour program. We should offer no more than 120 credit hours. Currently, we are at 124. About 20 years ago, we were at 134 credit hours. And at that time, we already thought we don't have enough credit hours to accommodate all these courses, these topics, etc. The other side is that we have a quite large number of credit hours dedicated to general education credits. So we have 39 there. So that means we have 85 credit hours to cover all of these things. And that causes some problems for us. We have tried to solve this by providing emphasis area or focus areas. We have, I think, 5 focus areas where we offer certain types of courses, and the students can go into that area or in that direction of their studies. Another problem that we face is at the other end of the spectrum. So the previous slide was for students graduating, going into an industry, etc. This is for students coming in. And our students who are coming in are quite often not prepared to take the classes that they are supposed to take in order to advance in 4 years through the program. And they also quite often, at least that's the impression I have a misconception what engineers do. This is a statistic, the Grave Bart thing statistic that we found a few years ago that was kind of interesting. It asked 2nd to 6th grade students, and this is a large sample size, it's 3,500 students. They asked them, what do engineers do? You have these categories given. You can see here, arrange flowers, sell food, make pizza. I'm terrific in all of these ones, by the way. And clean teeth, wire, install wiring, repair cars, etc. These are the topics that they found are a part of an engineer's work. We will be in big trouble if we have to cover these kinds of topics. So there's a general misconception already at an early age. What is engineering? What do engineers do? Another thing that we found, or what we think is happening, is that this misconception has some origin in the language that we use. Right now it's football season. If you pay close attention during the fourth quarter, they bring out the engineer because they have to make a comeback, right? Fourth quarter comeback. It's an engineering term, right? He engineered a fourth quarter comeback. It has nothing to do with engineering, but there are so many of these words being used to characterize something that is not a topic in our curriculum. I have a personal anecdote on this. When I first came to this country, I lived in Philadelphia, and I had a landlady. I started graduate school. I had a landlady, very highly educated. She came by quite often in the beginning and asked me, when do I get to ride the train? And I couldn't make sense of it. It took me a while to understand what she meant to it, but this misconception is there, and it affects our incoming students. They have a certain expectation that what they learn or what they will be doing later on. And so we have to work against that. Because I mentioned this problem here, so I want to give you a solution of it. I should have referenced this a bit more. The last one is actually from Wikipedia. It tells you what an engineer does in general. Very broad terms, obviously, but so I have to give you the answer to that. But what I want to focus on is more of the implication of culture and where this may come from. And this is materials, the first two graphs here, the pie chart and the bar chart. They are from the National Science Foundation, the Science and Engineering Indicator Report. National Science Foundation does every year a report. Unfortunately, they don't study every year the same thing. So this is from 2012 that I found was the latest that applies to this topic here. And so the pie chart, you see the 4 pies on the left-hand side is basically a chart that accounts for first university degrees by region or by country from 2008 to 2012. And it has these 4 circles there. They represent different disciplines. So the first circle is natural sciences. I don't know if you can read that. It's very small written. I screenshotted that from their report online. The second one is social science. And then in the lower, the second row, you have engineering and non-science and engineering. And we are, the United States is the black slice of pie, all right? So how many, in terms of percentage, are we producing in that field? And you can see, oh, by the way, light blue, medium blue is European Union before Britain exited, I suppose. Dark gray is Japan, and then light blue is China, and then you have a light gray is Asia 8. Asia 8 is an agglomeration of Asian countries such as India, Malaysia, Philippines, etc. So 8 of those ones. I want to compare those because there's some interesting things happening, I think, that affect or that indicate why we have problems with engineering recruitment. First of all, in social sciences, this is where we do really well, right? There's a 19%. That's pretty close to what EU has or other countries have. China is not doing so well there. It's 11% of graduates they have in social sciences. Then you go to non-science and engineering, and the slice gets smaller. Asia 8 becomes much larger, right? China is still very small, but then when you go to natural science and particularly engineering, you can see China is having quite the production here, especially engineering, 34%. And then Asia 8 is 17%. So more than half of all engineers produced are from Asian countries. And the United States is very small, it's only 4%. So we have a very small slice of the production in engineering in general. And so this to me indicates some cultural problems that we face here, that we are not able to attract students into the program very well. I have another chart here from the same report, the one in the middle here with bars. You can see the students coming to the United States pursuing studies are predominantly from these countries that do very well in engineering. So you would see that reflected in our programs. And so I wonder how much of that is reflected in the pie chart here, these 4% engineering students, how many of them were actually foreign students? I know this one has Saudi Arabia. This is 2012. That's right at the onset when we had this huge influx of Saudi students, when our small program suddenly had 500 students in the program for a while. Many of them were from these countries. So this reduced quite a bit again. But, you can hear China is there, South Korea, India is there, and that's accounted for in this 4% as well.
Marco,
yes.
can I just jump in just really quick? We're getting a little feedback, I think. Do you happen to have 2 computers on by chance?
No. No.
Is anybody else hearing feedback, or is it just me?
I can hear that too, yes.
You can.
I can hear that feedback too, yes.
Interesting. Hold on, Susan. Let's see. Oh, I don't hear it now.
So I have to stop talking. That works great.
Well, that's not going to work.
I'm so sorry for that. Yeah, I have only one microphone right now.
Okay. Well, continue on, and I'll see if I can fix it on our end. Sorry.
No, thank you. Thank you. Okay. Here are some other numbers, and I want to bring another problem that we face. You can see here the number of degrees awarded in engineering with all the different disciplines. You see here mechanical engineering in the United States, by the way, is the largest number. It's because it's the broadest discipline. So our students, they go on into aerospace, biomedical, nuclear, etc. And that's why you find a lot of these students here to begin or do a bachelor's degree in mechanical engineering. But what I want to point out here is this diagram on the bottom here. You can see here a distribution of distribution of male or female students in engineering over the years. And it's again from the same report that ended in 2012. And you can see 81% is male in engineering and 18% is female. This is a huge gender gap. I can tell you for the last 19 years that I have been at ISU, we have never been double digit. We are well below the national average, which is already missile. And so this is a big problem. We leave out a huge pool of talent that could come into our discipline and contribute. And NSF has spent a lot of money trying to address this. And I don't think anybody has come up with a solution. This is, by the way, not existing in Asia 8 and China. You have a much more even distribution between the genders in engineering. And if you think about, well, it's indicative if you look at the master's degree. So here's again the distribution of different disciplines. And you can see mechanical dropped quite considerable because they went into specialized areas. But you can see here the gender gap. You have now 77% male and 22% female. There's an increase. And I suspect this is because we have more foreign students coming to a graduate program than to an undergraduate program. But it's still terrible, right? I mean, it should be 50-50. When we looked at this, and Nancy, you were part of this, this was a grant we looked at a few years ago, the NSF grant. We found this statistic. You can see here on the first chart, here's engineering is always around 20%. For some reason, computer science has joined us. But then you have psychology, biological science, agriculture, social science, etc., with the exact opposite problem, right? So this is a problem that we face here too, that we try to address. It's not something that you can see an impact immediately, and we'll talk about that in a second. I want to talk about one more problem that we face. That is perception of difficulty. This is a chart I got from a book that has listed a statistic about how many hours students spend studying per week. It has 2 time points in 1961 and 2003. I don't have anything more new than that. There's a couple of interesting things, and I have no idea how to answer that, but it appears that our parents may have studied a lot more. If you look at the blue bars, they spend a lot more time studying, and our current students or immediate past students, they are so much smarter now and can study much faster, I suppose. I don't know the answer to that. But what I want to point out here is engineering is considered as too much work, too difficult, etc. But look at the variation. There's not much variation. Every discipline spends a lot of time studying, trying to do coursework, etc. So this is a misconception that is out there that I don't know how to address in this talk here. But it's there, and we have to face that in the recruitment. So this is my summary here of problems. It's not very popular, engineering in the United States as in other countries. Limits our recruitment. There's a definite large gender gap that we have. Students are not as prepared to enter engineering as we wish them to be. It's manifest by not being able to take some of the math classes that they need to start the program. So they end up taking a lot of gen ed classes because they can start with these ones, but it delays their graduation by a year or two. So we have a program that that takes on longer than we wish it would. I mentioned the credit hour crunch. We are still over the 120, and we don't know how to address that either. And then I mentioned engineering is generally misunderstood and perceived to be a difficult study. So these are the problems. There are many more, obviously, and I haven't listed them, but I thought these ones are worthy to mention. I want to talk about some of the solutions. This is an origin of all of these ideas here. This goes back into the 1990s. I worked at a university in the Midwest. I had a colleague. We were both young. We were both members of the American Society of Engineering Education. We have no formal training in education, right? So we were members. Our university subscribed to that organization, so we got the journal from it. We came across an article in that journal that was reporting a program that the University of Hartford created. It was called Design Around the Curriculum. And we went and tried to find every detail about this design around the curriculum. But what they were doing was that every class they offered in their program had a project associated. And that project may have been simple, but it was directly related to the theory with a practical application. And this is nothing new, but what they did then was that every class was building on an overall system. So this was a piece of a puzzle of a larger system. And while they learned as details for each class, they also learned through taking multiple classes the integration of these projects, the integration work of making these things to work together. And so at the end of their 4-year studies, they took home a complex integrated system that they engineered, they calculated, they simulated, they built, and fully understood. And I thought that was fantastic. My colleague thought that was fantastic. We were excited. We were thinking, okay, next faculty meeting, we take some PowerPoint presentation, we present that to our colleagues, and we're going to do the same thing. Next faculty meeting came around, we presented, we looked around, and there were a lot of faculty. They looked like me now with gray hair, but with closed arms and shaking their head. Nope, we're not going to do this. So we were pretty deflated, of course, right? But there was another faculty who was very interested in that. So we pursued this idea with 3 of us. We thought, okay, we have a certain number of classes that we control. We're going to build something like that. So we worked out a flow chart. We worked out all kinds of details. We went ahead, actually submitted an NSF proposal. This is when you had to submit hard copies, like 21 copies of it, and ship them by FedEx. And obviously we got rejected. But we implemented this to a number of courses, and we ended up with an integrated laboratory that integrated some of these courses. And it worked quite well. There were some issues. This is just the time when internet became more and more feasible. This is before Google was there, right? I mean, you didn't have the option of Googling things. But this is the origin of this entire talk here, to bring projects into classes. And that's what I've been doing since joining ISU. I have every class that I teach a project associated. It is not integrated with other classes, but I'm focusing on other things. And I've listed here, they're individual projects. I'm not trying to do too many things. Group projects, they are handled in another class, in their senior class, where they learn how to talk, how to operate in a group, how to be effective and productive in a group. I took that part out. I have only individual projects. And but I'm trying to practice the engineering approach, and I'll talk about what that is in a second. That's the main focus. I want to bring the theory and how it is applied and how is it affected by doing projects. Excuse me. And these are open-ended projects. I have never repeated a project. Every year I come up with a new project, and I'm running out of ideas. And there's a problem with this. A few years ago, I gave a project that involved a washing machine. They had to design the drive system of a washing machine and the suspension system, etc. And it was not stimulating. They were not engaged in that. So the type of project you come about is quite important. Okay, so I have some misses here and there with different projects, but I like to do new ones because it is more interesting to myself too if I have a different project each year. So the engineering approach is basically this: that before they do build anything, design anything, draft anything, I want them to first characterize that. I want them to model this using math. So they have to use their differential equation class and model the system, deriving the equation of motion, and then once they have the equation of motion, solve them, and then take that and program that. All right. And so they integrate the programming skills, and they can try to visualize what the response of the system is from a mathematical point. So there's nothing designed, nothing built, nothing tested. It's purely on the simulation side. What they can do now is they can now play with the parameters of the mathematical model that have a direct implication on their design. So they can optimize, and they can see and learn what is the influence of certain parameters. So how does the system behave? So they're gaining a deeper understanding about the system that they are trying to create before they're creating it. This they could go on here with iteration. I stop them usually. I say that this is good enough. Let's proceed because it can take too much time if they try to optimize it. And so once they have done that, they can start designing it. They can draw up parts. They can figure out what are the parts. They can build it, test it, etc. And at these instances, you have this iteration going on. I don't know if you can see these little arrows. So after simulation, that's the one iteration they have to optimize. And then after building and testing, they can iterate too, but I limit that because that's when it becomes costly. Now, these systems, they don't look like much. Let me show you a picture here. You can see here this big diagram or this picture here. You can see a computer screen, right? And then you see cardboard, and magically you don't see duct tape. This is, I think, dryer tape or so, but almost 99% of all projects, they end up having duct tape. Cardboard duct tape, this doesn't look like an engineered system. We don't care about that component. Okay, we try to look at the physics and make that to realize the physics of it. So this particular example here is basically a pendulum. See this bar here, and there's a motor with a helicopter propeller on it, and the pivot point is a potentiometer. This is run over a microcontroller, and then we run this into a computer so we can observe. And they have to design a controller, and so they have to mathematically model all of this. They have to program microcontroller, they have to program the computer, etc. But you have now options to bring other things into it that is beyond what we cover in the course, but that is of interest to them. For example, in this class, this is a controls class, I teach them how to write simple apps on Android-based phones. And then I teach them how to communicate over Bluetooth to this microcontroller. So they learn these components there, and then they can play with their phone, which they're anyway on all the time, right? To interact with their system. And so you create more interest by bringing other things in there, even though they're not software engineers, right? They're poor mechanical engineers, but they have now a little ability of bringing something else in it and make their interest in it. Here's another thing that I do. This is a class I don't teach very often. I try to create competitions. This competition here, this project was basically they had to build sumo robots. I think you know what sumo robots are. They're basically sumo. They basically push each other out. Excuse me. And so the objective is you have two robots in a ring, and you try to push the other one out. The trouble is they're autonomous. There's no remote control in there. I apologize, my voice is, it's not the echo, this is my voice here, I apologize. So they're autonomous. So what happened here is they have to find their position in the ring by themselves and broadcast it. And the other guy does the same thing. So each one of them knows where they are. And then they have to come up with a strategy how to push them out. So they have to think of how do I control that? And let me see if this video runs.
I think you get to go up against the losing members of DV.
So I can't grade this. There's just no way to put a grade to it, but there's instant feedback from the students. I had a tough time to make this video because they were all engaged and all interested in it. And what happened here is this one team, they figured out to do a very quick algorithm, while the other team, their robot was still thinking, and they were probably done when it was already out of the ring. So they had instant feedback from the competition, but I don't include that in the grade. What I do is I manage the project by having milestones and deliverables throughout the semester. In the beginning, when I did this project, I didn't do that, and I caused a lot of stress at the end of the semester because students would just push things off. We do that too, and they were overwhelmed at that point. So I have milestones where they have deliverables. They are either reports, they're either presentation, or both, and they get feedback at that point, so I can make corrective measures throughout, and I use that for my assessment for grading. Oops. This goes back to the gender gap. Nancy Devine from Physical Therapy, Occupational Health. I always mess up the departments. It's one department or two. We were part of a grant. There was an NSF grant that looked at rehabilitation of stroke victims using virtual reality. We developed programs or apps that allowed to do training for upper body disabilities. But part of that grant, we had some wording in there to address the gender gap. And it's basically from this chart I mentioned earlier, where you have a large gender gap in engineering in terms of many more male than female students, and in physical therapy, it's just the opposite. So the two of our classes met and discussed problems, culminating into projects that the engineering students had to solve. So the physical therapy students, they came with ideas and problem statements and what needs to be addressed and how it needs to be addressed, and then the engineer had to come from the engineering side to find solutions. And they met throughout the semester, and the students worked on these projects, and Nancy and I, we met once in a while with the students to get progress reports. And these are some of those projects that we had. The upper right one here is a stabilization device. I think I forgot what it was called. It's basically a thing that you put on your back, and if you lose if you lose stability, or if you fell over. I'm not sure quite anymore what exactly the situation was. This device was activated to help you stabilize your stand. It looks dangerous because it is dangerous, because these are massive motors and you have inertia. So we actually never strapped that thing on, but we simulated, we tried to build a prototype of it. This one down here, I'm actually sad we didn't pursue this further. I saw recently this commercially available. This was a posture control device. You can see here a baseball cap, and then on top of the baseball cap, we have a prototype of a microcontroller and sensor. Basically, we try to estimate what is your posture, and if your posture is bad, it sent you a message to your phone. And you're most likely looking at your phone when your posture is bad, right? So we will pursue this. We should have kept on working on this, because now I think these things are a product. This one here was a bit of a massive problem. We tried to build a quad bike for paralytic people so they can go mountain biking. This had a functionality that generated energy when you go downhill and used the energy when it goes uphill. We haven't finished this. We still have things to be machined. There's still one student from that class around who wants to finish this, which I really appreciate. So we have almost finished, but it's not there yet. And then this project here, you see a powered wheelchair. This is actually still going on. This turned into a graduate project. The objective of this project was is to make autonomous driving in a hospital or on campus, where you use basically a camera. In this case, we use an Xbox Kinect camera, and then use AI machine learning techniques to identify what's around you and then control the pathway. And so we're working actually on machine learning, deep learning, that kind of stuff with graduate students to do autonomous driving of a wheelchair right now. So this one is still going on. This hopefully finished. These ones are no longer pursued, unfortunately. Another thing we did on this grant, Nancy, you were part of this one too, right? This was a week-long summer camp. We tried to address these two issues of misconception what engineers do and the gender gap. And we found some statistic or some paper, I think, that related that students in 2nd to 4th grade are already influenced on what they will study later on. And so we wanted to do a teacher camp. This was a week-long teacher camp for 3rd and 4th grade teacher to work on their curriculum to bring in these issues of physical therapy and engineering. I think we had both, right? So we addressed physical therapy, what do physical therapists do, and what do engineers do, and how do you bring that into a curriculum? This is 2 years ago. This is not something we can assess if we had any effect. It's a long-term thing, and it would have to be much more broader. Nonetheless, it was interesting. It was a fun thing to do, and see how the teachers actually think about these topics. Another thing that I found that students are mesmerized by is catastrophes, disasters, things exploding, anything bad, except if it's their grade or their test, okay? And so I teach this, I don't teach it that often, it's a computer simulation class. I came about this, thought, okay, let's reverse the whole thing. We don't design something and analyze it. Let's take something that blew up, that massively failed, and play detective and find out, can we pinpoint the source of failure, and then go back to the literature, the published literature, and find out, are we there? Are we where what we found out? And that approach works great. And I let the students decide what kind of disaster they want to find out. So I have a number of these different disasters here listed. I want to point this one out because this was amazingly accurate in terms of the finding. This is the Havilland Comet 1 airplane. This is 1950s. It was the most modern jet plane, commercial jet plane at the time. It was so modern that it even had rectangular windows. You don't see that in any airplanes nowadays. And it had the habit to fall out of the sky after a few starts and landings. And so they stopped flying that. And one of my students, she wanted to investigate what happened there. And so she modeled that fuselage, and she looked at stress concentration of these corners of the windows and saw that there are cracks that propagate. And so she did a statistical analysis, created a model, did the statistics on it, and got some mean values and standard deviation of failure in terms of how many landings and how many starts. And then we went back and looked at these cases here. I mean, she was right smack in the middle of what actually happened. So that was instant reward. You know, you see, hey, it worked. It's not some abstract. We don't have an airplane like this standing around. We just have computer simulation stuff. But we could tell, yes, we're right on. So these kinds of things are very interesting to students. I offered this twice this class. I don't offer this very often. This is somehow, the Titanic is somehow fascinating to students. It's rather a boring problem. It's just a rivet that failed because of poor material and poor temperature. But students want to investigate that. They may have watched the movie or so. But there are other things that students come about. This is the Apollo 13 disaster where they model the tank and how it ruptured. And then they can go back to NASA reports where they actually have all documented in terms of pictures and in terms of analysis, etc., and compare that. We have students who go further back. This is something that happened in the 40s, the Cleveland, Ohio gas explosion. There's not much literature out there. So their investigation is more on what were the codes, the standards, and how do I apply that to design this, and then based on that design, what could have failed, even though we don't have much of documentation about it. This may be something you have seen. It's also popular. This is the Tacoma Narrow Bridge. It's a popular YouTube video where you see a bridge in Washington failed. It was in the 1940s. Basically, this is a bridge that was constructed in a valley, and you had wind going through, and it was designed in a particular way, and it caused excessive vibration and ultimate failure. We are able to replicate that. We look at the flow analysis of the wind crossing the bridge and see the stresses that occur. So the students have all kinds of different projects here that they found themselves. I don't have to come up with a project. So I think I'll leave it at that. I want to talk about one other thing that's not a disaster-based, but it's just as stimulating and engaging the students. This is a class that I teach every year. It's a mechanical systems design class, right in what I'm talking about, where they design machinery. And I have to come up with ideas. And again, I leave out washing machines nowadays. It's difficult sometimes to come up with ideas, but anytime I have a company coming in, the students are so much more engaged. It doesn't matter what kind of system it is. They believe now it's a real system. They want to impress the company. The company comes in and actually looks at the final product, the final presentation, and helps judging me this stuff. But the students are so engaged with this kind of stuff. So I always love to have companies coming in. The trouble is their timeline doesn't fit our timeline. And so this particular design here, this is a few years ago, was from I call it mom and pop shop. It's basically a family who started a company making some devices, and they want to automate this. So they had a garage where they had everybody employed in their family to produce this day and night. And we designed a machine who can replicate or who can automate this. And it was fascinating. Students building, first simulating and then building prototypes, because we couldn't build the real thing. This is way too expensive. But they built prototypes with little parts, with Lego and etc., to demonstrate the feasibility of their design. So yeah, this is a great motivator for students. So this is a summary of what works and what doesn't. So I mentioned just the industry. If you bring new skills outside of their study, competition worked well. class reviews and feedback, like in terms of distributed throughout the semester, where you give feedback so they can make alteration, they can change the course. And it's not too late to do this. That has to be implemented. And comprehensive projects with simple mechanism work too. I mean, it doesn't have to be a rocket or something like that. It can be a simple mechanism that is comprehensive, though, that addresses all the or many of the topics that you try to cover in class. What does not work, I didn't talk about this, large class size. I mentioned that we had, for a period of time, 500 students in our program. With 6 faculty, it was unmanageable. There's one class, I had 45 students in it, and I have to meet with each student half an hour each week, and it's just one class, and so it takes enormous amount of time, these large classes. Thankfully, we're much smaller now. I don't think the university appreciates that, but I think the quality goes up. I mentioned non-interesting project, and this is hit and miss. I do not know. I mean, I know now washing machine doesn't work, but I come up with an idea, and I cannot predict if this is of interest to students or not. So I don't have a mechanism for coming up with good projects unless they are from industry or they have disaster implemented. And not all projects work out. I missed to mention that sometimes we fail in this. Okay, it's not everything works out. And this is real life. We don't get everything to work. We don't get to solve all the problems. One thing that I have to be very careful when I do this approach, I have to align my lecture material with the project tasks. This is a bit difficult because the project task I'll lay out at the beginning of the semester. And then the class starts and questions come in or things happen, and my timing of my lecture topics deviate from my original plan. And so this becomes all adaptive. I have to work this throughout the semester. But I do make these intermittent submission of tasks and feedback work. One more thing that I don't even know what is the timing here. Just the one last item I want to talk about is assessment. I teach control, so feedback is important. And I want to assess how effective these things are. And I have not found a way to assess learning. There might be something out. There are plenty of tools to assess happiness, but learning is somewhat difficult. What I do periodically is, for example, something called a knowledge survey. It's not really a knowledge survey. It's a very simplistic questionnaire where I list all the topics that I want to cover in that class. And so you can see here there's like 33 topics I'm going to cover in this class. And I ask them, how do you feel about it? So it's not knowledge, it's a feel good kind of thing. Do I understand that topic? I don't understand this topic, or somewhere in between. So I have 3 choices, and I do that at the beginning of the semester. Then I do it at the end of the semester, and I compare. Was I effective in this topic? Do I need to spend more time in this topic, etc.? It is not something that the students benefit from because the semester is over. So it's then the next year that I can apply that. I don't do that every year. I do that once in a while. And I chart these things out, and I can look at the area, and it can tell me what I need to do. We have an overall assessment because we're an accredited program, EBIT accredited, where we have basically we have 3 program outcomes that go into 11 student outcomes that trickle down into every class, where we look at certain things that we want the students to be able to achieve. And so that is ongoing. That's every year that we do, and we adjust and try to improve. It is very structured and descriptive from the accreditation board, and they change once in a while. We have some disagreement, I think, as faculty compared to what they are trying to impose, but we have to abide by this process. So there's an over-assessment that occurs. I think that's all I have. I'm happy to answer any questions, or I'm even more happy to have any feedback on ideas and comments.
Marco, oh, go ahead, Nancy.
So I had one question kind of from the beginning, in which you were identifying the need to reduce the number of credits you're trying to cram in while covering all those topics. Do you know if anyone ever looked to see, as you reduce the credits, whether there was a change in the pass rate on your exam by your students, on the engineering exam?
Yes, that's an excellent question. We statistically significant we were during the time when we had a large influx of international students. Unfortunately, they did not take the EIT exam. So we missed out on the opportunity to get a really large number. But traditionally, we have done well, our students have done well on this exam. It's not a very rigorous exam. The licensing exam 4 years later, that is pretty serious stuff. But the EIT exam is not very difficult, so they do well on it. It's not a true test, but we still feel obligated. We need to cover this stuff. And yeah, but yeah, that's a good question.
I'm curious. So yesterday, actually, a couple of the colleagues who we were having this conversation with are in the room, but we were talking about student choice and how powerful student choice is when, you know, engaging in meaningful learning for students. And your examples are so excellent of ways that you give students choice on the disasters that they investigate, things like that, which can be tricky. So when the students in your class pick, you know, a catastrophe or something like that they're analyzing, do you find the literature for them to research the topic, or do you give them, these are the requirements for the literature? How do you structure that choice piece so they all are looking up equitable research and background, things like that?
Yeah, that's a great question. I didn't address that. So what I do is they have to give me a proposal at the beginning of the semester. And they may do that research, but quite often they don't do the research. They think, oh, this is cool, I want to do this. And then they submit it, right? And I have to evaluate, is this, you know, has that the level that I want to achieve, and is it the same as other students that they propose? So I'm the regulator of these things. They could do a lot of research and find out a lot of things, but they usually don't. They're fascinated by the explosion or whatever it is, the instant of things. Yeah.
Thank you.
I have a question about some of the information you provided early on about the gender imbalance in engineering. And I'm wondering, as a faculty member in an actual classroom, do you ever talk with your students about those sorts of issues, about women in the profession, and engage them in those bigger conversations?
No, I have not. So a typical class that I teach has 30 students in it, and maybe one female. Of those 30 students, one female, and the rest is male. And that puts a lot of pressure to that one person if I bring something up. And I try not to single out people, or I mean, it would be a great resource to talk to the students directly. I understand that, but I try not to single out, or yeah, I stayed away from that. I've never done that.
I can understand why, especially if there's only one person in that class, that it would be really difficult. And I've got to assume that your students notice this imbalance. So I'm just trying to think what I would do, and I can't imagine a way that I would bring it up, but I also, it also is curious to think if students might have their own ideas about ways to make changes in the profession as on a larger scale. I don't know. Anyway, thank you.
No, no, I totally agree. This is the source of knowledge right there, right? We want to access it. We want to find out, but I don't know how. Yeah, that's a good question.
Okay, yeah, Marco, I was just going to bring up that Lawrence Beatty, the retired director of the Energy Systems Center, did some research on this topic because it's another field where women are underrepresented. And he found that if you could get in a class, if you could get about 25% of women or some other minority, that then they felt really comfortable and would persist. And if you had lower than that percentage, then your extraordinary ones, of course, are going to stay on, but your average ones are going to have a harder time of it.
That is very interesting. And we worked with Lawrence. I miss him. We worked on measurement control and trying to integrate his expertise with our research center. I don't think we ever get to 25%. As I said, we were always in single digits since I have arrived here at ISU. My previous university was the same, by the way, in Indiana and in Michigan. You had maybe 10% or something like that. It was better than here. This is extremely poor showing what we have here in Idaho.
So just interestingly, so I'm a physical therapist, right? And I think my entire 34 years as a physical therapist, my profession has been 70% female dominated, right? But fascinating, for our accrediting agency, we always kind of get docked for lack of diversity in the group, but we get some consideration that the majority of our class is male, and that's incredibly unusual. So if you came to our program, you would think that physical therapy was male dominated, and in our group it's the women that are the minority, which is very strange within the profession. So it'll be interesting to see how long that necessarily would it influence the West or our culture or whatever it is, but we attract more males than females, but it's not representative of a profession at all.
And is there a cause for that? Do you know how can you trace this back to something or?
I think there is something culturally right where we live in which more men pursue advanced education than women in fields that are lucrative, if that makes any sense. So I think some of it's because we're a graduate program, so I don't know how to say what an undergraduate program would look like. But with our graduate program, I don't know how to address this, but we've very, very rarely have we had a woman who is of the dominant cultural religious group in the area. So where the vast majority of our male students are from that religious background. Not all, right? But so there is some mix, but I wonder if the potential salary to offset the cost of going to graduate school and the role of women and what they do and how often they start having children, et cetera, influences that. And again, we do have women, but it's not even close to the national standard.
Yeah, very interesting.
We have time for one more question. If anybody has a burning...
I have a question about like your project. So my name is John. I'm with a Karen Appleby, same department. So I have a very similar class that my student need to do like some individual research project at the end of the semester. So as you said, your student need to turn like a proposal at the very beginning of the semester. Is it correct?
Yeah. It's a few weeks into the semester, I would say. Okay. They get some exposure of what they're getting into. And I lecture on some of the topics, and then I'll let them loose.
How many times do you meet like with your student, like to provide feedback for that project?
So the classes that are more heavy on the design, I meet them every week, individually, half an hour. Where classes that are less on the design, such like the controls things that I showed you, I don't meet that often. I have just regular office hours where they can come in and present their problems. I also have great support with a TA in these classes. So the TA is, we built many of these projects just before the semester starts or right at the beginning of the semester to make sure we know exactly what difficulties get into it and we know it's working. And so the TA actually has worked these problems out to some extent, and so he or she can help with the students as well.
Thank you.
Thanks for the question.
Well, Marco, thank you so much. That was an awesome presentation. I think we all learned a lot. So let's give Marco a round of applause.
Well, thank you so much for the opportunity and for listening to me. I appreciate that very much. Sorry for the echo or whatever that noise is. It's probably, I'm still teaching asynchronously and it's bouncing off the walls here. So
At some point, I didn't even hear it anymore. So we're all set. It was no problem.
Awesome. Well, thank you so much.
You are welcome. And thank you all for coming today. We hope to see you at upcoming events. And I will have Marco's recording or lecture recorded and up on the PI website. And if you have other questions, I'm sure it would be fine if you email him too. So thanks everybody and have a great weekend.
Thank you. You too. Bye-bye.